Greetings to all the moderators and everyone who is watching this video. My name is Lim Wilson. Today, in this international conference on computational intelligence in machine learning, I will represent my group, which includes Dr. Anis, Dr. Uswah, and Dr. Bibi, to present our paper titled Defect Severity Classification of Complex Composites based on Guided Ultrasonic Wave Signal using Deep Learning. In this presentation, there are several sections will be discussed based on this flow, which are Introduction, Literature Review, Research Methodology, Results and Discussions, Future Work, and Conclusion. So, what is a complex composite? Complex composite is a combination of two or more materials arranged in particular patterns and quantities to achieve desired material properties. It is widely used in aerospace and automotive industries because of the composite has higher strength to weight ratio and higher tolerance to fatigue and corrosion compared to the other materials. The composites such as carbon fiber reinforced polymer and metal matrix composites also have more flexibility to fit with the design, thus leading to a higher efficient structure. However, composite structures are prone to internal defects like delamination due to their layer-by-layer construction. In comparison, cracks in metallic structures usually start appearing from the surface of the structure. Additionally, unlike metals, composite materials are usually brittle in nature, leading to unstable crack propagation upon failure. When there is a low-velocity impact on complex composites, the damage is barely visible and hard to detect. It is dangerous as the damage like delamination at initial stage will spread to the entire structure after a period of usage. Secondly, the current techniques for defect detection are still time-consuming and expensive as it required large inspection team. For example, in aviation sector, if the examination cannot complete in a scheduled time, the aircraft service will be affected. In this study, there are several objectives need to be done. First, to analyze guided ultrasonic wave signals of complex composite defects. Second, to develop a database on complex composite defects in terms of signal and image. Third, to propose an accurate classification framework for defect classification. Last but not least, to evaluate the performance of the proposed system. There are some topics are needed to study in this project, which are complex composites defects, guided ultrasonic wave testing, signal analysis method, and deep learning for classification. There are several types of damage usually found in complex composites based on previous paper, which are void and porosity, delamination, fiber fracture and misalignment, matrix cracking, and fiber debonding. To detect the damage above, non-destructive testing is the most frequently used technique in industry. In this case, we will be using the guided ultrasonic wave testing to collect data of composite defect. Based on the previous study, the testing consists of transducer tools and ultrasonic transmitter and receiver with guided high-frequency sound wave between 1 kHz to 30 MHz, which can detect flaw size and crack location efficiently. The third part is about signal analysis method. From previous study, there are two methods commonly used for defect detection. They are Fourier transform and continuous wavelet transform. Both methods are selected for study because the signal can be viewed in time and frequency domain for better analysis. The plotting is then become the image dataset for deep learning to classify the defect. In this case, the convolutional neural network or CNN is studied as the method is suitable to classify image database. The CNN consists of convolution layer, rectified linear unit, pooling layer, and fully connected layer. Convolution layer puts the input image through a set of convolutional filters, each of which activates certain features from the image. Rectified linear units allows for faster and more efficient training by mapping negative values to zero and maintaining positive values. This is sometimes referred to as activation because only the activated features are carried forward into the next layer. Pooling layer simplifies the output by performing non-linear downsampling, reducing the number of parameters that the network needs to learn. And lastly, fully connected layer flattens the metric into vector and feed it into a fully connected layer like a neural network. Next, I will explain about the research methodology. There will be three phases. which are signal preprocessing, development of deep learning network, and classification model testing. In Phase 1, the dataset of raw ultrasonic wave signal from data collection team of Dr. Anis is used, and the dataset consists of 6 different sizes of defects. They are 10mm, 20mm, 30mm, 40mm, 50mm, and 60mm. The analysis on the characteristic of the signals is done based on fast Fourier transform and continuous wavelet transform. Then, one of the methods will be used for the image database construction and labeling. In Phase 2, the development of CNN network is done based on the pre-trained model available in MATLAB, and the best parameter of training option is determined through the training progress. In Phase 3, the testing dataset is tested with the classification model to determine the model's performance and accuracy. Now, I will present the results obtained throughout the semester. In the figure, you can see that the raw signal at sample 100 of each defect size is converted from time domain to frequency domain using fast Fourier transform. The result is not satisfied to become the image database, as the graph is too small and need to zoom in until become the figure at the right, and the other parts of the graph cannot be seen. The other way to have a better view is matching the graph with time, which will be shown later. As I mentioned previously, there are 2 methods used for the analysis to form 2D image, which are FFT and CWT. The result later will choose whether which method is more suitable for this study. After applying FFT with meshing on sample 100 of each defect size, we can see that the difference of color distribution is not obvious except for 10mm. Same to this result, the FFT image of 20mm defect size also don't have much obvious difference in color distribution. The difference is the yellow space of each image increases when the number of samples increases in the same size. When it comes to CWT, the images have more significant difference at the shape of contour and the part at behind which looks like tail. Then, for the CWT images of 20mm defect size, the images are quite consistent in the shape of contour, but the tail part is a bit different. Same to FFT case, this is due to the amplitude of the signal is different when the number of size increases in the same defect size. After having the results for both FFT and CWT, we can compare that the CWT have better viewing because of the extra characteristic on contour shape and the tail for CWT compared to the color distribution only for FFT. Moreover, the color in CWT is easier to observe compared to FFT. So based on the comparison, the image of CWT method is chosen to become the database for deep learning. Before proceeding to deep learning, all images are split into training set, validation set, and testing set. Then, the training and validation set are augmented with 0 to 360 degree rotation and X and Y reflection. After the training and validation of the CNN deep learning network, we can conclude the performance as in the slide. Among GoogleNet, ResNet 50, and Inception ResNet V2, Inception ResNet V2 performed the best with 99.12% of validation accuracy and 0.0341% of validation loss. Then, the model is tested with different number of epoch and initial learn rate for training option. After the experiment, 200 epochs and 0.01 initial rate performed the best with 100% of validation accuracy. Next, the model is tested with training set, and the figure on top right is the example of the classification result. The testing set with 10 samples for each size are classified successfully with the average accuracy of 99.77%. The testing performance of the model is calculated from the confusion metric in terms of precision, recall, and F1 score. As all samples are correctly classified, the precision, recall, and F1 score for all classes achieve 100%. From the result, can conclude that the model is feasible to be future applied. There are some future works need to be done in the next semester. First, to add more challenging database with different defect size and location. Second, to develop more mature deep learning model for the classification with more features. And third, to evaluate the performance of the proposed model with more testing set, as the testing set during this semester is less due to the limited resources. Below is the Gantt chart for the whole final year project. The progress is still keeping on track until now. In conclusion, the result shows that continuous wavelet transform perform better 2D imaging than fast Fourier transform with more obvious difference. The most suitable CNN model is Inception ResNet V2, and the parameter for training option is 200 epochs and 0.01 initial learn rate. The result also shows the training and validation accuracy at 100%, whereas the testing average accuracy at 99.77%. That's all from me. Thank you.